Thanks. Quantum error correction is what makes quantum computers vastly more powerful. It enables people to implement way more quantum operations than you could do without quantum error correction. The last 12 months, we've seen incredible progress in implementing quantum error correction across the field. I've been working in quantum for the last 2 decades, and this is just such an exciting time to be working on quantum error correction. So I want to today just give you an idea of what we're building at Riverlane and the trends in quantum error correction that we're seeing over the past year or so, and kind of what to look out for next. Right, so I wanted to start just by motivating quantum error correction, and I would say quantum computing in general. Computers are used to design new products in many industries. The Wright brothers at the turn of the century discovered flight through trial and error, but today the aerospace industry uses computers to design new products. And the reason they can do that is that we have a great model of the world, the Navier-Stokes equations, and we have computers that can solve those equations. But when we try to do the same, for drug discovery, so the simulation of an organic molecule and how it interacts with a protein, or how battery material, or how electricity moves across a material to develop a better battery, or how a catalyst reduces the energy consumption in an industrial process, there's a problem. We hit a wall. We have this great model of the world, it's called quantum mechanics, but we can't solve the equations. We don't have the computers to solve the equations. When we, approximately speaking, add one more atom, we need to double the size of the computer. So quantum computing could change that, right? Could radically change what's possible to simulate, and therefore what's possible to design on a computer where we currently discover new things. And that's why quantum computing will revolutionize multiple industries, from healthcare to advanced manufacturing, address major challenges such as climate change. But there's a problem here, which is that the best quantum computers in the world can perform on the order of 100 to 1,000 operations before errors in the device overwhelm the computer. Right, so quantum computers are currently extremely noisy. We need a 10,000x reduction in the error rates even to get started in some of these hugely impactful applications. So the solution to that is quantum error correction. It's a technology that sits on top of the qubits, and essentially what we do is add redundancy. So just like classical error correction that's all around us in mobile networks, for example, we take multiple physical qubits and assemble them into a smaller number of logical blocks. Right? So this extra redundancy means that if any one of the qubits fails, you can still recover. So quantum error correction is an idea that's been around right from the beginning. I think people understood the importance of quantum error correction in the field, really in the early days. If you're from classical physics, you look at the state space of a quantum computer and it looks suspiciously like an analog device, this block ball. We know analog computing is more powerful than classical computing, but it's extremely error prone. And so the ability to do error correction in quantum computers is fundamental to the entire field. So the challenge is how to implement quantum error correction. And of course, there are 2 key things that you need for that. So one is the qubits to be sufficiently good. So you need many physical qubits. And what I want to talk about is the second thing you need, which is the classical compute that is running error correction whilst the quantum computer is running. So what I've shown here over on the right-hand side is the clock cycle of a quantum computer. Right, so down at the bottom you have the physical qubits, and what we do is we measure some of those qubits to get syndrome data, so error data. This tells us something about what went wrong in the quantum computer. But it doesn't tell us exactly what's gone wrong, it just gives us some clues. So that data is passed to the decoder, as we call it. This is essentially solving an inference problem. So given the data, what's the most likely error? The decoder then makes a decision, sends back a signal to the control systems who can then make a correction. So go flip some of those physical qubits, the ones that we've decided to have an error. Right, so this cycle happens between every logical operation on a quantum computer. And so it needs to be very fast. Right? It needs to be operating at a rate of megahertz. It's the rate limiting factor in your in the clock speed of the quantum computer. Moreover, the amount of data that's coming out of the quantum computer is really vast. So at 1 million physical qubits, we're talking 100 terabytes per second. That's like Netflix global streaming. It's going to be coming out of your quantum computer, and you need to process that before you want to do anything else. And so the only way to solve this problem is to build dedicated QEC chips. So just as GPUs were used to scale up AI workloads, so QEC chips will be needed to scale up quantum computers. So this is what we're building at Riverlane. In 2023, we released the world's first QEC chip. It's DD1, so it operates at megahertz. So it's a 4 megahertz chip processor. It implements a highly efficient, highly advanced decoding algorithm, so it has a logical error rate of 1 in a trillion. So we can take 1,000 physical qubits and turn those into a single logical qubit with an error rate of 1 in a trillion. It's also very small in size and power, right? And this is going to be important because as we scale up, we need many of these chips. So we need approximately 1 QEC chip per logical qubit. So we need thousands of QEC chips all working together. So their size and power consumption is going to be important for the future. So just to kind of put this into a bit of context, like if you think of the stack in a quantum computer, just expanding the bit of the QEC stack here. So at the bottom, obviously hiding a huge amount here, but the physical layer, the physical fabric of the physical qubits, on top of that is an analog readout, so analog to digital readout. So that's in the control electronics, and that's either generating microwave frequencies or it's controlling lasers, depending on the specifics of the underlying physical qubits. The QEC stack takes over at the digital level, so once those signals have been turned into digital signals of either or specific syndrome data. So that data then needs to be moved to decoders across the fabric very, very quickly so that the decoders can all work together to solve the inference problem. And that then enables user programs that are written in your favorite quantum programming language to be compiled to both physical qubit architectures and the decoding architecture. So there's a classical compute problem that's running alongside the quantum computer. And that, of course, then means you have the scope to implement algorithms. So this is kind of just put a bit of context into where is the QEC stack within the quantum computer. So there have been huge progress in the field over the last 12 months. I would say in kind of 2 main buckets. The first is on physical qubits, and I'll talk through the progress that we've seen in implementing or in improving physical qubits. And the second is on the QEC theory side and the implementation of QEC. So we've seen things like better codes that are reducing the overhead. Just a result here that we have from Riverlane showed that by improving the quality of the decoder, we could reduce the number of physical qubits that are needed to get the same logical error rate, right? And so this is saying that by better understanding how errors show up in the quantum computer, we can build a quantum computer that's 5 times smaller than we previously thought, right? So these are really meaningful advances in the field because it brings forward the date at which we can build a really useful quantum computer. So just then on the trend in terms of like why now, I think these results in quantum error correction theory are really significant. And then the second is on the physical qubits. So I'm showing 2 plots here. One on the physical error rate. So this is on your left-hand side. So this is a log plot, and I think this is the closest that this community gets to a Moore's law is showing that approximately every 12 to 18 months, the quality of the physical qubits doubles. Right? And that's super important for quantum error correction. If you remember, we're adding more physical qubits in order to use redundancy to correct errors. Of course, if your physical qubits are just incredibly bad, then adding more of them just makes the whole system worse. So there's this notion of a QEC threshold. And once you get to that threshold, then your physical qubits are now good enough that error correction can start working. And indeed, we saw spectacular results from the Google team just recently showing that QEC was making the number of logical operations was greater than the number of physical operations by adding QEC. So going below that threshold typically results in diminishing returns. So by the time you get your qubits good enough, the key thing then is to scale up the number of physical qubits. And so the second plot shows, again on a log plot, the number of physical qubits that have been demonstrated, either in experiments or the dashed lines show the roadmaps of quantum computing companies. Now, of course, it's extremely complex, and doing the two things at the same time is one of the things that makes this really hard. But I just want to give you a sense of why now is the time for QEC. Why is the community so excited about QEC? So looking ahead, so our roadmap, we've demonstrated that we could decode at megahertz, so we can keep up with the data generation rate of the qubits. This year, we're releasing Deltaflow 2, which will enable us to stream data continuously through a system and maintain a single logical qubit up to 10,000 operations. We're then adding logic to that, because of course we need more than just a single logical qubit. So this is kind of how we step through complexity into where we really want to get. And that's what I want to talk about just to finish, which is the megaquop era, so million quantum operations. That's what we're looking to support by 2026. We have designed our roadmap to match the roadmaps of the leading and most aggressive quantum computing companies, so that Deltaflow can be integrated into their product as they're building it. I introduced a bit of jargon here. I mean, number of QOPs, so quantum operations, and million. Like, why should you care about both of these numbers? There are lots of metrics out there, and I think actually as a user it's quite straightforward. You care about how fast your computer runs, and you care whether it runs at all, so whether it fails before completing the computation. Whether it fails or not is this reliability metric, and that's what we're talking about in terms of QOPs. And so it's simply, if you take your quantum circuit, so that's the algorithm you want to run, you take the number of qubits multiplied by the depth. That gives you a good metric of roughly how much compute you're doing. The number of QOPs needs to be bigger than that for this to run reliably, at least to a good approximation. And so the QOPs is just 1 over the logical error rate. And the second plot shows approximately the cost of implementing error correction. We're currently in this gigaquop, like 1,000 quantum operation era right now. And where we really want to get to in terms of the next major milestone is a million QOPs. The exact resource requirements are going to vary, and people are still working on reducing these resources. But the key point here is once you get error correction working, you can really then start to scale through gigaquop and teraquop. Right? I mean, these are where the really big applications are. So megaquop is a really exciting milestone for me, and I think for the field. And it will be the first time that quantum computers really go beyond the frontier of classical computing. So if you compare the performance of a megaquop quantum computer to a classical computer that's trying to simulate it, you end up with just outrageous figures, right? The performance requirements for the megaquop quantum computer can perform 1 million error-free operations, about 100 logical qubits. That's about 10,000 times more than current quantum computers. It's going to solve problems very quickly, and importantly, using a very small amount of energy. in comparison to the huge supercomputers you would need if you wanted to simulate this quantum computer. So this is taking the best like-for-like simulation, and of course there are other things you could do in terms of algorithms, but if you just wanted to brute force simulate this, then you would need just a totally ridiculous number of GPUs to simulate this quantum computer. And so that's why I see this as the quantum computer that goes beyond the frontier of classical supercomputing. It's actually unclear what you can do with this quantum computer. And I think the exciting question for you, just to finish, is this is coming. If you look at roadmaps of companies building physical qubits, we are developing the classical compute that will run alongside that. Within the next 3 to 4 years, this is going to be available. So what are you going to do with it? Thank you.